My name is Zhong Lin Wang from Beijing Institute of Nanoenergy and Nanosystems and Georgia Institute of Technology. My presentation today is on Maxwell equations for a Mechano-Driven medium system moving with acceleration. First one, I'll explain to you why we need expanding the Maxwell equations. We have developed a new technology which called triboelectric nanogenerator, TENG, use which we can convert mechano-energy into electricity. As you can see, compared to the traditional electromagnetic generator, we utilize triboelectrification effect. The output is linearly proportional to frequency. In contrast, the electromagnetic generator, which give an output of proportional to the square of the frequency, especially its output voltage is also proportional to the frequency. So at a low rotation speed, its output voltage is rather low. So the TNG has the advantage of a high output voltage, and which can in fact convert a tiny mechanical energy into electricity. The difference is that the electromagnetic generator is used circuits which cut the magnetic field. The TNG utilizes two medium which have a relative movement. So the medium have movement, and this gives you a different situation compared to the conditions under which the traditional Maxwell equation was derived. So let me show you the results of the two. So if you can see, this is the output of the TNG, which give you output of the current and voltage. And this electromagnetic generator, which give you output low voltage, so we have to run a high frequency in order to observe anything viable. So therefore, TNG has an advantage for converting tiny scale, low frequency mechanical energy into electric power. So we have received a number of data which shows that the TNG can convert to mechanical energy into electricity, but more importantly, it can run at a high frequency. For example, use MEMS-based devices. We can run this TNG at a frequency up to 1.18 megahertz, which is high enough to give electromagnetic radiation due to media motions. So the media do have a motion which give you a electromagnetic leakage current as well as the displacement current in a space. So then we can utilize a rotation TNG, which use the medium rotation, can deliver power wireless to a small distance. In this case, that the output power is generated by the displacement current generated by the rotation medium. The medium is rotating, which gives you an alternating current in space. And such a case gives us the hint that medium motion can generate electric magnetic wave. It can also deliver power. So you can see the light, which is located a few centimeters away, can be lit up. So this was the first few examples shows that the medium motion can generate electric power. The third example is that we utilize the triggering of a mechanical force on a TNG-based device. Use mechanical triggering, which can deliver wireless signal to a distance about 10 to 20 meters away. This shows again the signal can be generated due to mechanical triggering. Again, this is not due to current oscillation, but due to the medium movement. That's why we have to expand the Maxwell equations. Most recently, we have another set experiment that uses sonic wave to trigger a TNG. The TNG generates a displacement current which delivered to the electrode. An electrode go through water a few meters away to reach a receiver, then receiver do the control. This uses a sonic wave trigger TNG, which generate an electromagnetic signal, which transmitted wireless to some distance and then be received, give the possibility for underwater the signal transmission. You can see this one uses sonic wave, and then we can generate the TNG here. The TNG deliver the sounds to a distance over here.
Right.
Okay. can see the students give a sound. So it's a mechanical tricking give you electromagnetic radiation. Then the other example is the finger tapping. Okay, finger tapping. You can see the finger tapping here is a TNG generator signal, which generates the signal here and then transmit wireless here. All this does not need external power, but it's the mechanical motion. That means medium motion can be able to generate electric power as well as the signal. So what's the principle of the classical electromagnetic generator? Classical electromagnetic generator is such: use a magnetic field, the coil cut through it, give you Lorentz force drive the electron flow in the metal rod, give you a voltage drop as well, current here. So this is called conduction current. What we observed is different. We call the displacement current, which was first proposed by 1861 by Faraday, by Maxwell, excuse me. And then this is the conduction current and the displacement current. If what's displacement current? According to Maxwell, it says displacement current is not an electric current of a moving medium, but a time variation electric field. That means it's not an electric current of moving charges, but a time variation electric field plus a contribution from the slight motion of a charge bound to the atoms. Okay, so in our case, it's different. We not only have the variation field, but we also have the medium motion. So the medium is moving, but this moving boundary was not assumed when we derived the Maxwell equation. Okay, so you can say that this is something we can introduce a small correction to the electromagnetic wave equations we normally utilize due to medium motion. So let's look at this moving boundary conditions here. So that's why we have to expand the Maxwell equation based on our most recent observation based on T and G. Now let's look at the Maxwell equations. What's the condition under which it was derived? Okay, if you look at all the textbooks, Jackson's textbook, and even the most recent book by so-called modern electrodynamics, the equation was just given and did not specify the conditions under which this full differential equation was derived. So we just take as is, receive as is, without thinking its assumption based on which the equation was developed. If you look at the Feynman's book, and he said that this is the differential form of electromagnetic induction here. And this is the integral form, is the line integral of E around a loop equals the time derivative of flux of magnetic field through the loop, which if you explain that into the mathematical equation, this is what it means. So this gives you the time derivative of magnetic flux is the circulation of electric field. But we need to introduce medium motion in those equations and see what's the difference we made. If you read furthermore in Feynman's book, and he said that use the flux rule. Okay, what's the flux rule? Is the electromotive force is equal to negative of the time derivative of the total magnetic flux. If you express, this is the term here. So if you have linear circuit, that means line circuits here, very thin wire approximation, then this works perfectly. However, if you have a metal disc, which is rotating at a sliding needle on the edge here, so this is basically the circuit. He pointed out this so-called anti-flux rule case. That means this is not valid for explain this case here. So in his book, he just wrote these two examples that's so-called anti-flux rules, but did not give the details why is such. So we explore the further details why is such and how do we include those large medium motion into the equation. You see the difference between here is the thin wire approximation. This is a large disk. It's different. That's the key for our following derivation. Sizable medium moving make a difference. So if you look at the four physics laws, Gauss's law for electricity, Gauss's law for magnetism, and Faraday's law of electromagnetic induction, as well as Maxwell's laws here. All this give you the physics laws for the Maxwell equation here. Let's take the third one as example. So this is the time derivative of the magnetic flux is the circulation of electric field. And this is the time derivative of the electric flux plus the total current is the circulation of the magnetic field. Now you can see this derivative apply to both. Apply to the field, can also apply to the differential units here if the surface is varying. Now if the surface is stationary, then you can directly switch the differentiation and the integral. You can switch that. You can be able to say, oh, direct apply to the magnetic field. This assumes the surface does not change. On the left-hand side, from here to here, you use Stokes' law. Mathematically, you can convert that. This is valid for any circuits. You can drop the integral for the ds. You can arrive at equation for the third equation in Maxwell equation here. But this was based on an important assumption, station medium approximation, fixed medium volume and boundary, no moving. That's what it is. But in our case, we have a different, the medians are moving, so we have to introduce a correction to the term in the Maxwell equation in order to account that. Once you have a medium motion, this is in non-inertial form because the motion can have acceleration. So therefore, if you use this transformation, like such a Lorentz transformation, you have to be very careful. Okay. Now, well, people look at the mathematical, the electrodynamic book. They say, well, if you have a moving charged point charge in space, its charge can use a delta function. Its current can be used a velocity multiplied delta function. Substitute to the Leonard-Windchild potential, you'll be able to calculate the potential in the entire space due to a movement of point charge along a trajectory. So this is known, but this is valid for what? For a point charge moving in vacuum. That means no other medium nearby, so you don't have to consider boundary conditions. That's the assumption for this. So this applies to a point charge like we have in an accelerator, but does not apply to a medium that have a size, shape, which even moving. So we cannot generalize this situation to a general case. Okay, then other people say, well, medium motion, they naturally assume constant velocity along a straight line. That's what you use in the special relative. If I saw relative, you have a move along a constant line and straight here. So that means basically an observer on an inertial frame observe an electromagnetic phenomenon in a lab space. So what do they see? They say, well, use the Lorentz transformation. Lorentz transformation is such. Let me do this again. Okay, you can see this is again. Lorentz transformation have a velocity, moving velocity, which is a constant, but it's a speed of light. Speed of light is in vacuum, is perfect, work perfect. But if you have a medium, partial space covered medium, so what is the speed of light for Lorentz for transformation in that case? I don't know the answer for that, but if you're in a vacuum here, the field you observe in a moving frame to the lab frame is correlated by this relationship here, which is known. But this does not consider boundary condition as we used to be. Okay. But in reality, in engineering application, practical applied physics, we have moving medium. We have several moving medium. They can have acceleration. They also can moving along different trajectory. And if we observe on Earth, what do we see? What I care is that I want to see those medium. But if you use Lorentz transformation, you say, oh, I need to know exact trajectory here, but here on Earth, I may not know the trajectory of this moving object. But what I care is, what do I see on Earth here? That's the goal I try to figure out. Especially, you have several medium you could moving. So what do we observe on Earth? So I must emphasize, we put everything on Earth. We are not consider universe because in that case, relativity effect is become very important. So now we elaborate the need, we elaborate the requirement. Now let's look at how do we develop the Maxwell equation for Mechano-Driven. Why do we call Mechano-Driven? If you have acceleration, you must have external force to drive it. So it's called Mechano-Driven medium system. For such a mechanical, electricity, and magnetism three-way coupling, the things become a little complicated. So if you look at the theoretical physicists, what they do is that on the full physics law use that integration format. By assumed station medium approximation, they derived the differential form of Maxwell equations for station medium. Then they said, oh, the observer can move using Lorentz transformation. They can get a relationship between the field observed in moving frame and in the lab frame. This uses Lorentz transformation, which is very nicely and beautifully and works excellent for any moving speed, but in most cases easy to be applied in a vacuum. And if you apply medium, especially boundary, it's not easy to do. So what do we do? In order to do this, we adopt Galilean transformation, which we can adopt this for engineering and apply physics for our purposes. And we can derive a set of equations. We include medium motion, electricity, and magnetism, and the wave coupling. All this are the coordinates are in the lab frame. That's what all this field is. What we observe on Earth when the medium moving, rather than move our observation on the medium and it turns back. That's not the way we do. We want to do everything in the lab frame. That's what we observed. So there's a difference here. Use this coordinate transformation back and forth. Okay. So there's two approaches. Approach 1, approach 2. Okay. Now let's look at the detail for this one. Let's see how do we derive this. We started from the 4 integral equations from the 4 physics law. First is Gauss law, is that the full integral of the electric field around a closed surface is the total charge inside the surface. A full integral of magnetic field around a closed surface is 0. That means no magnetic monopole. If you have an open surface, it must have an edge. The magnetic flux through the surface is this integral. The changing rate of magnetic flux is the circulation of electric field around the edge of this loop. Okay, if you have the Maxwell law, you say the flux of the electric field through the open surface plus total current through the open surface is the circulation of the magnetic field around the edge of this loop. So that's what's the physical meaning here. But we must be very careful. If this surface is fixed, you can do what we used to do. You can switch differentiation with the integral. But now, this surface is not. This surface is varying, expansion, contraction. We need to consider the time derivative, both apply to the field as well apply the boundary. We need to be very careful about this one. So let's do that. In such a derivation, we use 2 mathematical identities, which is the time derivative of the total charge with the volume. You can give you an identity here. This is the partial integral of the charge density plus the moving velocity of the medium of this surface. And this is the volume integral. This is the flux. The flux of C functions through a surface is time derivative. Is partial derivative of the function itself plus a few other terms. This is due to the moving of the surface. The surface can moving, and the contraction, expansion can be, this moving velocity is general. It can be time dependent, of course, can space dependent as well. So this is 2 mathematical identity. Somebody says use so-called moving field argument. That's wrong because they use the differential equation derived here. We use the integral equation here. We don't have the problem. So this is the mathematical identity we utilize in our case. So if you use this one for Maxwell's equation, the integral form, you'll be able to derive as following. For example, the electromagnetic induction become partial differential on magnetic field plus the Lorentz force term. This is the moving velocity of the medium of the surface, and this is the circulation here. And this is give you the partial derivation of displacement vector, and this is to the correction of the displacement vector, the velocity dependent term to the magnetic field. This is inside the medium. You have those correction terms. So those inside the medium. If you look at the space inside the medium, if you look at the outside medium, those terms disappears because outside is the differential equation for standard case, there's a standard Maxwell equation here. So where the two meets on the boundary, so inside we have this set of equation. On our side, we have this set of equation. We have to meet the boundary condition as such. Okay, so we utilize this first derived here. This is the standard differential equation or Maxwell equations for station medium. But if you assume the medium motion is a rigid translation, that means solid translation, you can have this is a d big D big T. This is the full derivative, have a velocity term. If you work on some mathematics, you can convert it into more general term here. So this is the new law of electromagnetic induction. This is electric field, and this is the magnetic field correction term. This is the partial differential of that, and this is the magnetic field, and this is the discipline vector correction to that term, and this is the current due to the moving point charges in space. Okay, now the situation we include such is the medium motion. The medium's motion, do consider about this. So we have a medium move back and forth. We must include that in derivative equation. Especially this movement can have acceleration, can faster, can vibration. All this has to be included in a derivative. We have made the two assumptions. Number one, low speed limitation. That means the speed of moving medium is much less than the speed of light. And this is excellent approximation for macroscopic object on Earth. The other one is we neglect the relativistic effect in space. So we don't consider relativistic effect because for on Earth, we can ignore that for most purposes. I'll come back to that later on. So you can see the moving medium, that's the case. Now, let's look at the further details here. If you derive the equation we see here, and this is the we call Maxwell equation for a Mechano-Driven medium system. This velocity is general. It can be time dependent and can be also position dependent. If you use this one, work on the total energy in the system. We came out with the total conservation of energy for the whole system. This is the changing rate of the density of electromagnetic energy. And this is the flux, the radiation flux, pointing vector to the space. And this is the power supplied by the current. Okay? This is the supply by the current here. And this is what the field, medium motion give you to you. So if you do not have medium motion, this term is gone. So you have the general concentration of energy between electricity and magnetism. But now if you have medium motion, you have the Mechano-Driven term. So Mechano-Driven, electricity, and magnetism, total energy is conservative. But just the electricity and magnetism, they are not. So this is different from the traditional electrodynamics. So we have to be very careful about this. Of course, if you have Mechano-Driven case here, the equation is not covariant, because you have external tricking. So that's why. So don't assume this Mechano-Driven case can be, Lorentz transformation can be covariant. They may not be, because the medium motion have a velocity dependent term here. Okay. Now let's look at another expansion, is the displacement vector. This is the field applied, and this is the medium polarization. This was first introduced by Lamar on 1897. He said if you have external field applied, the medium immediately responds with polarization and then due to the at atomic scale. So have negative charge on this side and positive charge here. So we have a P term. We add up to here, would be arrived at the permittivity plus the electric field. But this include only the electric field induced polarization. Now, if we have medium motion here, if you have the surface charge on the medium, this moving back and forth, you must include the motion produced polarization. We call Mechano-Driven polarization, which is this term. We call PS. So this is the Mechano-Driven polarization due to surface charge. Where the surface charge come from? Can come from contact electrification, piezoelectric effect in general. So therefore, we have the induction polarization and the Mechano-Driven polarization. Both terms are there. So we first time introduced in 2017 for this. Okay, so if you have a capacitor, they have a small leakage field at edge, but if you open one end of the capacitor, have a start more leakage. If you make two plates parallel, if you have oscillating current back and forth, this gives you electromagnetic radiation. Now, besides the current-induced oscillation, you could also have the medium. This medium can move. So you have both oscillating current and the medium motion give you electromagnetic radiation. All the result of this one being included in this equation. So medium motion can produce a source of current. Medium motion can have a correction to the field observed. So medium motion can generate electromagnetic wave. Medium motion can also be a way of power generation, which displaces the current you observed. So medium motion, all the things can be included here. But again, this is on the assumption of low speed move motion as well as neglect relativity effect. So this, you can both the PS and the D prime over here, and that's what we are more familiar with in our conventional derivation here. So this is the three-way coupling, Mechano-Driven, electricity, magnetism. Okay. So is this a conventional approach? Has been accepted in the community? If you are theoretical physicists, they have a different approach. They use the integral form of four physics laws on the station medium assumption that derive the differential equation here. They use Lorentz transformation to get the medium here. That's what they do. But this only works good for constant move velocity. If you have an acceleration, you have a changing trajectory, it's not, can be easily applied. So therefore, this is the case they utilize. In our case, we use Galilean transformation, and we work on a three-way coupling, Mechano-Driven, electricity, magnetism. We write a new set of equations. This is more work on field theory more towards unification of the four fields. And what we more here is for engineering electrodynamics, so more applied. So we can make some approximation. That's okay, as long as we can solve our problem in reality. Okay, so in our approach, in the engineering approach, is documented in textbook. In this textbook, 1941, Stratton put the equation like this, and he derived this the Maxwell. This the equation for electromagnetic induction. Do have a velocity term which is same as ours. Okay, then in different language, in this Chinese version electromagnetism, you do have this integral here. You can see this use the magnetic force. Okay, you can use the motive force to derive. You can derive the equation which is similar to what Strauss got here. So people have utilized this for decades for engineering purposes. So regardless which you use, as long as you keep self-consistent, you'll be all right. You'll be all right. So don't confuse one with the other one. If you keep self-consistent, you can deal with the case. So now we have a medium motion. Inside the medium, use the Mechano-Driven equation. So this is the Maxwell equation for Mechano-Driven medium case. But in a vacuum, we do have the standard equation here. So the two meets at the boundary here. So inside the medium, you can say, some people say, well, this looks like Hertz equation that which is could have the extreme speed of light. No. Inside the media, we have a refraction index. The speed of light is only a fraction of the speed of light in a vacuum. For low speed limitation of medium motion, there's no such a case exceeding speed of light, right? So therefore, inside the medium, we have the Maxwell equation for Mechano-Driven system we derived. In a vacuum, we do have this. Then both at the boundary meet the boundary condition, then you get a whole solution for that. So it's become very natural. If you have a few, you just do each individual and make sure the boundary condition satisfied for that. Okay, so let's make it simple. On Earth, we have our engineering applications. What we care is about the sustainable development of humankind. We can use our Mechano-Driven equations, Maxwell equation for Mechano-Driven systems here. But when the electromagnetic wave is generated, when the wave goes to space, you once it to the space, you do have the standard Maxwell equation which governs its traveling. So that's good, okay? Because on Earth, anything have a size. desk size, medium size. But when you go to space, it's not that. So in space, you have this, each star is like a point cloud, and the vast, you can consider each star as a point cloud. That's okay. Okay, that consider okay. So in the depends on the scale you talk about that. But in space, light travel like a turtle on Earth. Okay, so in such a case, you do. Let's look at that on Earth. Anything have a fast move velocity. I use this video here. And if you look at Mars, Earth, okay, if you look at universe, vast, okay, all this is what light travels many years to reach the other end. So it depends. Where do you look? If you look at the Earth, low speed works fine. And look at space, light travel like a turtle moving on the Earth. That's a different scale you move. So in the universe, we have to use relativistic effect for electromagnetism. Okay, so that's why. Let's have some discussions with regard to the approximation we get. First, let's look at Galilean space and time. Okay, somebody say we must use Lorentz transformation instead of Galilean transformation. The answer, for engineering purpose, we can use Galilean transformation. This goes back to 1965 by Leblanc. He proved that if the moving velocity of the medium is much less than the speed of light, and the Galilean phenomenon takes place in an arena, the spatial variation of which is much smaller with regard to the distance covered by light due to the duration of the event. That means if the spatial we care about that is much smaller than the time traveled by light during the event, during the duration of this event, light can go very far to the other side of Earth. That's very possible in engineering program. So on our engineering application, we can safely use Galilean transformation, which is an excellent approximation here. Okay, and Galilean transformation has been used by Europeans for many years. They call this 40 years of Galilean electromagnetism. They conclude that Galileo use this Galilean transformation, they can deal with electromagnetism of moving mediums and to a very good accuracy. And here's the conclusion from this review article. So Galilean electromagnetism is not a native to special relativity, but precisely its low velocity limit in electromagnetism. And this is 1 century after the seminal work of Minkowski. Electrodynamics of moving continuum medium is still subject of investigation for research and should be included in the physics lectures as well as early as possible. But we don't see this included in the physics book. Why? Because most of the physics book were written before 1970. And this was only included in 1973. So the textbook has not revised recently. So students forget about that, will not learn. So we teach students not only just for theoretical physics, but we teach students for engineering applications. So I think we should teach this part as well as our Maxwell equation for Mechano-Driven system case for general. You are training people for the humankind. So now let's look at the Faraday law of electromagnetic induction in a little details here. Okay, Faraday law of electromagnetic induction, according to Feynman's book, he say line integral of E around a loop is the time derivative of the full flux of the B through a loop. That's the, if you put it in this standard form, which is this one. This was the equation we utilized to derive our first set of the Maxwell equation for Mechano-Driven systems here. This is what it is, okay? But in the Maxwell equation here, then it says that, okay? But if you have Jackson's book, that's slightly different, okay? Slightly different for that. In Jackson's book, let's say, if you use the Lorentz law, you have the full magnetic flux and the time derivative of which give you the electromotive force. And this is electromotive force in a reference frame in which the point charge is stationary. So that means what? If you have a circuit, and you have a circuit, this point charge is on the edge of circuits, and in its rest frame, this is the electromotive force, so E prime. Okay, so this is the equation here. But in his text, Jackson is only deal with constant moving velocity. Okay, he say that physical phenomena are the same when viewed by two observers moving with a constant velocity with respect to each other. So provided coordination in the space-time are related by Galilean transformation. That's what he stated here. Then he used the electromotive force and correlated to magnetic flux. This is Lenz's law. Okay. Then mathematical, this is split in two parts. One is directly applied magnetic field, and direct applied to the surface integral. Surface integral give you this term. Remember, this V is the velocity of the circuit's motion. Circuit's motion, all right? Okay, so, but E prime is different. So E prime is the field in the rest frame of the point charge here. So let's look at this one. If you assume is an inertia frame, so the force acting the point charge in its rest frame is the same as the force acting on self in the lab frame. If these two forces equal, that means F prime equal to F must be inertia frame. That means moving is a constant velocity along straight line. If you have acceleration, that's not valid. Okay, so if you have E prime to E plus V, and this is what? This is the moving velocity of the point charge. So he put this in, this moving charge, the unit charge, if it equals the moving charge velocity of the circuits, the two term cancels. So he arrived the differential equation for electromagnetic induction. Again, this is in inertia frame, constant velocity, moving velocity. Number two, it assumes the moving velocity of the point charge is equal to the velocity of the circuits. But we look at this in detail, see is this the case or not, and what changed in the Feynman's case here. Let's look at it. If you have a large medium, if you have unit charge, if this medium is moving at a velocity v, the point charge can move differently because its total moving velocity is the velocity of the reference frame or medium plus its relative moving velocity with respect to the medium. So you have this term. So you substitute this here, but look at this electromotive force, this Lenz's law. Mathematically, this can be identical to this due to the use of the flux theorem for field theory. So you can derive this. This is the velocity of the reference frame moving or surface moving. But now if you assume this is the total velocity of the point charge. And you put in here, this is here, and this term, if you substitute here, be cancelled with this one, so you leave a relative velocity of the point charge with respect to the medium self. So that term remains. But now I have two cases. See which one this will contribute. Okay. Now let's the first case. If you have a thin circuits, the point charge moving along the circuits. If the VR is parallel to the circuits like this, DL. If this is parallel to DL, this term is absolute zero, drop out. So this term drop out in the integral, then you can use Stokes' law, you receive the standard format of differential equation here. So on the thin wire approximation, the Maxwell, the Faraday's law is correct. Faraday's law's the matter of differential equation is correct. But now, if you have a large disk, this disk is rotating, you have a sliding needle. If you look at this the constant magnetic field, the flux through the total circuit is not changing. So he found in this case, this is called anti-flux rule, anti-flux example. But in this case, the large and medium move because the point charge may follow a different trajectory with respect to the integral of the circuits. So this term remains. So therefore, if you have a large medium, especially have some conductivity, compared to the thin wire approximation, you have additional term in electromagnetic induction here. And this rotation have acceleration. So this remains in there. Okay, we'll come back to this one a little bit. Okay, so we have two cases here. Now, in Feynman's book, he have the anti-flux rule. This is the case obeys the electromotive force rule very well. But here, if you have a disk, you have a sliding needle here, changing here. It appears the total flux does not change, but you do have a medium rotation. There's a sliding. That means the structure of the circuit is changing. And this is a 2H doing like that. Also, does not obey the total flux rule here. So let's do a little more discussion on this one to explain this anti-flux rules as Feynman quoted. Okay, the first one, if you use the electromotive force, use Lenz's law, this is given, but the total magnetic flux, the time derivative, is the electromotive force. The next one, if you do mathematically for this one, this looks like exact. Only assume the structure of the circuit does not change. That means you can expand, you can contraction, but no sliding, no sliding. No, that means hardwired, okay? And this electromotive force here, these two should be identical but different. If you have a blade like a fan shape, it rotates in the medium like that, this is suppose the total magnetic flux does through the metal blade does not change. That means it should have a zero. But in reality, we should have a potential drop from this end to this other end. And this is anti-flux rule here. The reason because in this one, we have a change. The Lorentz force acting on charge, you have a potential drop here. Okay, if you use the moving velocity here of the point charge, you put it here, you do the calculation, you find the electromotive force there. Okay, now let's look at another case. If you have a disk which is rotating and this line on H, if one point charge just kind of here, if you follow this trajectory of this point charge as the disk rotating from time 0 to time t, this point charge move here to here. So disk already rotated. So the point charge move from here to here, from here to here. The disk already rotated from here to here. You can see the area covered by this little segment is the change of magnetic flux. That's the one. So this is the virtual change in magnetic flux give you the electromotive force. If you look at geometrically, nothing changed. You are not supposed to see the electromotive force for this case, but we do experimentally. So the reason this discrepancy comes is for these two equations because this large medium rotation have acceleration, rotation have acceleration. So this term, this equation here looks the same as this one, but they can have a difference. So therefore, in the reality you plot, you have to be very careful. This assumes no change in the structure of the circuit, but this can have a change in the circuit here. So this example explained to you why do we have a large medium, motion medium. If I use point charge, we don't have this problem. Medium means have a size, have a shape, it can rotate like that. So that's why we have to revisit the Maxwell equations for Mechano-Driven system if you consider the motion of medium here. Okay. Now, in the relativity, special relativity, you have a point charge, you have Coulomb field in this one. This is what Bob says. If Alice is moving in a constant velocity along a straight line, what she saw is this, have electricity and magnetic field here. So same phenomenon observed by two observers. And these two observers have no relationship. That means no interaction. That's what the special relativity is about. In our case is that we only sit on Earth in a lab frame, and the medium is moving, and this moving velocity can have an acceleration. So that means you can be along complicated trajectory. And these two medium have size and shape, can have an interaction here. And if the force acting on the unit charge in the lab frame is the Lorentz force, its force in its rest frame is QE prime. In general, F prime does not equal to F. In order to make this equal that one, you have to assume it's inertial frame. So this Maxwell equation would derive for inertial frame for constant moving velocity, one with respect to the other one. So this can be equal. You can derive that. Again, this should be the velocity of a unit charge, not the moving velocity of the circuits or the medium. But if in general case, the two are not equal, so therefore, if you have an acceleration case, medium's motion, you need to have to be careful. You have the electromagnetic induction law is subject to be expanded. So is Maxwell equations. That's why we have to do this piece of work in the last few years. So be very careful for the two forces acting on one same charge. They should be equal if it's an inertial frame. If not, they are in an inertial frame due to accelerated motion here. Okay, so this is the reasons why we have to expand the Maxwell equations if you have accelerated medium motion here, because Maxwell equation was derived for stationary medium. If you have a moving medium, you must be expanded for that. This is, I believe, is the truth. Okay, so if you have these two cases here, that's why for moving mediums, but what's Bob see? He saw the medium in his own reference frame. There's other medium in the other one. Two can have interaction. What's the field he saw? Is a solution. This is called Maxwell equation for Mechano-Driven case here. He can utilize this for his purposes, right? So this is good. We can utilize this for his purpose for that. So this is for engineering purpose, which is good. And again, media are materials. Media are not collection of point charge. They have volumes and boundary. This has to be very careful. This is why the Leonard-Windchurch potential cannot be applied for the medium case. You have to make the solution meet the boundary condition. The Leonard-Windchurch potential works good for in a vacuum for infinite large space. So what is the speed of light used in Lorentz transformation in the case of C and D? That means you have partial medium field space. You use Lorentz transformation. What is the speed of light here? We don't know. Things to consider. So this equation gives you a good description of Mechano-driven electromagnetic system three-way coupling, including the Mechano-driven position term we have introduced. Okay, so now let's look at the detail here. If you from Stratton's book, fine book, they say the circulation electric field is total flux, the changing rate of total magnetic flux. From the Jackson's book, say the changing rate of magnetic flux is the circulation of the E prime. E prime is the field in the reference frame of the point charge in which it is at rest. That means the circuits, on the circuits. This too appears differently, but you can derive the Maxwell equation for Mechano-driven system based on this. You can also develop based on this one. Make sure you are self-consistent. As long as you're self-consistent, I believe the result will be very close, right? So let's say if you have electromotive force is the reduced rate of total magnetic flux, and this is the Lorentz law here, and use the mathematical, this term becomes over here. Only in inertial term, the Lorentz force acting on point charge equals the electrostatic charge when it is in the rest frame. In such case, that means uniform motion. The velocity is a constant. Then you have F prime equal this. All right? And in such a case, you can substitute the E prime by E plus V. This is the moving velocity of point charge. It may not be the velocity of the circuits. So this is V naught. But the velocity V is the total velocity, is the circuit's move velocity plus the reference velocity. Together, you substitute in left-hand side, you have this term. This is the medium motion term, and this is the relative motion term. On right-hand side, this is the medium or circuit motion term. These two terms cancel with each other. Then this term remains. So therefore, if you have a large medium, there's a relative rotation between the point charge, especially rotation here. This term remains. That's why you have to expand the Faraday's law for electromagnetic induction. If you have acceleration, right? If the moving velocity of unit charge is the same as the moving velocity of the reference frame and inertial frame, some people assume this in that derivation, but remember, have a condition, which means that you assume this equals 0, you get this one. So this have a condition on this two inertial frame as well. The moving velocity of the relative moving velocity of the charge could be 0 or parallel to the thin wire approximation. If a large medium, that means the velocity is 0. All right. So if you have acceleration motion, F does not equal F prime because of accelerated movement of medium surface boundary. The Faraday law of electromagnetic induction is subject to be expanded, and so is the Maxwell equations. This is an important conclusion we reached so far. Okay, now let's do the summary. there's two space and time. The first one is special relative space-time. That means the field in a stationary frame and a transformation, Lorentz transformation, you can get field in a moving frame. Of course, you can get this one, but only on a special case for constant movement and in a vacuum case. But the beauty is that this works for any moving velocity. Okay, I mean any maximum velocity, you can have a close speed of light, but it's constant, constant. So that's why the inertial frame you can do that. The other one is absolute space-time. It's called Galilean space and time. And two approach. One is in Galilean electromagnetism. The field in each frame, in the lab frame, on the instantaneous quasi-static approximation. So the field are calculated frame by frame. That's called quasi-static approximation. And this works for low speed, but in inertial frame, also assume constant velocity. They have used these constitutive relations. So on the electric limit and magnetic limit, the equation gives Galilean covariance. So Galilean electromagnet provide an effective approach for engineering and physics for solving a large number of electromagnetic phenomena. It works, okay? The other one is the Maxwell equation for Mechano-Driven slow-moving system we have developed. This works for any moving velocity as long as its magnitude is small compared to the speed of light. Can be a time dependent or can be time and position dependent. This is working for liquid and softer materials. We also introduced the mechano-polarization term, which is due to medium motion here. So I believe our equation here is more applicable than those existing ones for medium, especially if they have acceleration. Somebody said, well, we can use the instantaneous reference frame to solve the problem. Yes, theoretically you could, but only through numeric calculation. You cannot do that with analytically as the equation we write down here. So therefore, you may be subject to some mathematical difficulty for that, and that you have to be very careful. If you have medium, have a boundary, that's not easy to be done, okay? Because this works in a vacuum, not easily be done with in a system have a boundary, have a shape for that. So one has to be very careful for these two cases over there. So we published a few papers on this one. I can refer to reader for that. This is a review on our TNG, triboelectric nanogenerator, and in which I also give the derivation of the PS term as the theory for quantification of the output power of TNG. And this is the first one we run on expanded Maxwell equations used for rigid solid translations. So rigid translation means you can have time dependent on the moving velocity. And this other one is arbitrary velocity, and with case here. We also wrote a 2-1 for Chinese for the in Chinese language for other readers to be easy to understand. The last one is that I have an in-depth understanding about the Faraday law electromagnetic induction, which is up to date with my understanding as I present here, the thin wire approximation, the large medium approximation. How do we include the anti-flux rule case in the Maxwell equations? That anti-flux rule case was first pointed out by Feynman, but did not include those in the Maxwell equation. We now can include that the anti-flux rule case in the Maxwell equations case by case. So I think that's the expansion to Maxwell equation for that. So look at what we can learn. 1831, Faraday discovered electromagnetic induction. 3 years later, Lorentz promoted the Lorentz law. Okay, this is very important, put mathematically. 1861, 25 years later, Maxwell put it into equations, but of course this format of equation were not his original 20 equations. This was done until 1897 was put in a form people are used to that today. Then before that time, people didn't realize was important at all, and people don't believe that until 1808. Hertz saw the electromagnetic radiation through this arc discharge and also the oscillating circuits for the first time proved the existence of electromagnetic wave. Ever since then, everything exploded. So you can see from the simple electromagnetic induction, you never dream this can see the electromagnetic wave, but through almost 55 years effort. So you can see at the very beginning, we have a phenomena, then we can go theory, and we can verify the theory and develop something which is extraordinary or unknown. So therefore, we have to be open-minded from the history of science. So we invented piezoelectric nanogenerator in 2006, the TNG in 2011, and 2017 we first introduced the Mechano-Driven polarization term in the Maxwell equation here, and this gives you output current and voltage. Then last year we introduced this into the fully integrated Maxwell equation for Mechano-Driven system and include our recent work. I think this is more comprehensive, include everything. Looks complicated, but it can solve the problem for the reality. Sometimes put this equation too simple, doesn't mean it looks too simple, but you have to, for the calculation, could be difficult or impossible if you consider the full boundary conditions as we present over here. So therefore, it is a field we observe on the lab frame if you have a number of medium move in the nearby, right? Okay, so anything happen afterward? I don't know, but we have to be open-minded from the history of science. Many things could happen, could be useful, could be important, but I don't know, which remain to be discovered. So, right, this is just my own outlook and perspective to the future. So, inside the medium motion, we have the Maxwell equation for Mechano-driven system. Outside the medium in vacuum, we have the standard Maxwell equation. Both meet at the boundary here. That's why you see solve the electromagnetic problem on Earth. In the universe, of course, you can treat Earth like a point, and you can use this standard thing here, which of course obeys the special relativity and preservation of speed of light, the invariant of speed of light. So I think the two meet at the boundary, each governing different zone. This governing inside the medium, this governing outside medium, two meet at the boundary. That's the whole solution of the system for that. So in conclusion, first one, in a vacuum, there is no need to expand the Maxwell equation, regardless if there are medium or not in the nearby. That means if I look at the space, the field in a vacuum, there's the medium around. If this medium is moving or not, it doesn't matter. I still use the standard Maxwell equation. But now, if you look at the inside the medium, they have a finite size and a volume. The newly derived Maxwell equation for a Mechano-driven system has to be utilized, because in this case the medium is moving. I look at the field inside the medium. So you have to divide this by zones, the zones inside the medium and zones outside the medium. The total solution to meet at the boundary. Okay, so for electrodynamics of macroscopic object on Earth, we talk about macroscopic object, not on electrons or those tiny particles on Earth. For engineering application, one needs to use the Maxwell equation for Mechano-driven medium system if there's a medium motion, especially you have acceleration. So therefore, this has to be included in case. So we believe Maxwell equation should be expanded. And if expanded, what else can be affected? I don't know. You can consider case by case. We work on engineering purpose here. We are not on field theory. And as long as the problem on Earth, that's what we do about that. But in a vacuum, you can use the standard Maxwell equation. You don't have to worry about the change of shape or revision or expansion for that. So last, we introduced the surface Mechano-driven produced medium polarization term, which is the additional term display vector here. So standard Maxwell equation give you the electromagnetic wave. Expanded the display current give you the theory for nanogenerators, which give you the current and voltage out power. And we use the Maxwell equation for Mechano-driven system here, which include the field we generate here. So therefore, what we care about here is one guy see two interaction mediums, both in two different reference frames, and one moving with acceleration with respect to the other. That means one person see two phenomena. In the special relativity, is two observers see one phenomenon. So that's the difference. Two persons moving in a constant velocity, one respect to the other, see the same phenomenon. But this one is one person see two interacting electromagnetic phenomena in two reference space that could have an acceleration for that. So things are a little more complicated than that, right? Okay, so with that, I'd like to thank you very much for listening to my talk, and I appreciate your time, and also, of course, your questions are welcomed, and we are constantly working on this problem. Hopefully, we are improving and offer you something useful, okay? Thank you very much.